Hello everyone, I'm Takanori Fujiwara from IEEE VIS. Today I will be talking about a visual analytics framework for reviewing multivariate time series data with dimensionality reduction. Multivariate time series analysis is becoming increasingly important in many application domains, such as healthcare and car transportation. As seen in the emergence of the Internet of Things, the size and dimensions of available data are becoming larger, and this makes the analysis of multi-time series data more challenging. To analyze such large and high-dimensional data, dimensionality reduction is frequently used as it can provide succinct overview of the data. Existing dimensionality reduction methods such as PCA and t-SNE are designed to apply to a matrix. However, in multivariate time series data, multiple instances which have multiple variables change their values over time, and thus it is often represented as a third-order tensor. As a result, we cannot directly apply existing dimensionality reduction methods to the entire data. Therefore, typically the researchers slice the data along a time axis, then apply dimensionality reduction to each slice and show each result with animation or juxtaposition. Another approach is computing each slice's dissimilarities with a certain distance measure, and then producing the dimensionality reduction result based on their dissimilarities. Slicing can be applied to the other axes as well. For example, we can perform a slicing the data along a variable axis and follow the same procedure above. However, these existing approaches have several limitations. When there are many slices and we use animation or juxtaposition, it is difficult to find important patterns such as similar temporal patterns and outliers. Applying dimensionality reduction to dissimilarities of matrices does not have this problem. However, when computing the dissimilarities, this approach mixes up different axes such as time points and variables. As a result, we might not be able to find any useful patterns that are highly related to a specific axis. For concrete example, please refer to our paper. Additionally, both approaches usually have limited support of interpretability of the results. To overcome these limitations, we designed MulTiDR framework, which has two major functionalities. First, MulTiDR framework provides a two-step dimensionality reduction. Unlike the approach using animation or juxtaposition, the two-step dimensionality reduction uses all axes to produce the results. Also, it handles each axis separately. Consequently, we can avoid mixing up different axes. Additionally, we support interpretability by using contrastive learning with an interactive visualization. In this approach, we can provide algorithmic support to understand dimensionality reduction results. I will now explain the details of each functionality. First, I will explain the two-step dimensionality reduction. Here, we have a tensor of t time points, n instances, and d variables. We first apply tensor unfolding, which reshapes the input tensor to a matrix of n times t rows and d columns by arranging vectors obtained from slicing along both the time and instance axes. Then, we apply dimensionality reduction to the obtained matrix to reduce d columns to one column. After that, by referring to the index information of time points and instances, we can produce a matrix of n rows and t columns. The purpose of this first dimensionality reduction is to compress the multiple variables to one representative variable, while preserving certain information as much as possible. For this step, based on the analysis purpose, we can select a linear dimensionality reduction method. For example, we can use PCA to preserve the variance information, or LDA to include the differences from the other tensors. Now, we can apply any dimensionality reduction method to this produced matrix. This step produces a low-dimensional representation for visualization purposes. Again, based on the analysis purpose, we can select any method for this step, such as PCA, t-SNE, and UMAP. For the rest of the slides, I will use PCA and UMAP as the first and second dimensionality reduction methods, respectively. In the previous slide, we obtained instance similarities by applying the first and second dimensionality reduction to the variables and time axis respectively. Because we apply the second dimensionality reduction to the time axis, the obtained results show the instance similarities mainly based on temporal changes. Similarly, we can apply dimensionality reduction in a different order. In this case, instance similarities are mainly based on distribution differences in variables. For example, when we analyze the US air quality data, we can obtain two different dissimilarity results of US counties. On the left, the second dimensionality reduction is applied to the time axis. So this shows the similarities of counties mainly based on weekly changes of air quality. On the other hand, on the right, the second dimensionality reduction is applied to the variable axis. As a result, this shows the similarities of counties based on overall values of air quality measures across time. Similarly, we can obtain different results of similarities of time points and variables as well. Now, I will explain how MulTiDR provides interpretability. We first provide the related context of points showing the dimensionality reduction results. For example, when we analyzing similarities of US counties, we can provide location information. By linking these views, we can show which counties are included in each cluster. For the further analysis, we usually want to know the characteristics of each cluster. To support this task, we visualize the features contributions to characteristics of each cluster. To provide such information, we utilize contrastive learning. More specifically, we use CCPCA with our new sign adjustment algorithm. Please refer to our paper for more details. We visualize feature contributions corresponding to each dimensionality reduction result. In this example, this plot shows each week's feature contributions. The magnitude of the value represents the strength of the contributions, and each sign shows whether a cluster tends to have higher or lower feature values compared to the other points. Here, we can see the blue and orange clusters have different peaks in their feature contributions. We also show relative frequency histograms of selected features to compare value distributions across the clusters. We can see that when a cluster has a high feature contribution, we can see more distinct distributions. We also want to know the meaning of the feature values. For this, we visualize weight vectors that the first dimensionality reduction uses to generate the representative feature. In this example, we can see that all measures except for ozone have similar weights. Thus, we can say that the feature values are close to the mean of the four measures with similar weights. In summary, we provide three pieces of information to support interpretability of the two-step dimensionality reduction results. Now, I will demonstrate one representative case study. In this case study, we analyze a dynamic contact network of high school students. From the network, we extract the variables with DeepGL, which is a network representation learning method. DeepGL produces 10 features which consist of node attributes, network centralities, and others. As a result, we obtain a tensor of 30 time points, 180 instances, and 10 variables. From the obtained tensor, we identify and characterize different groups of students. The right result shows the similarities of students based on node features. Here, we select several distinct clusters to analyze their characteristics in more detail. From the node link diagram, which shows all communications throughout the entire period, we can see students in the blue cluster are located in the strongly connected regions. In contrast, students in the teal cluster have only few connections to others. In the feature contribution view, for each network centrality, the blue and orange clusters generally have strong positive contributions. By selecting several features, we can see that the blue and orange cluster tend to have high higher values compared to that of the others. This is especially more salient for the blue cluster. From the weight vector, we notice that these generated features use large weight around the morning, whereas evening have close to zero weight. MulTiDR seems to effectively prioritize the time when students have actively contacted each other more. From the analysis, we can say that during school hours, the students in blue cluster play a central role in communicating to other students as they have higher values for various network centralities. Now, we further categorize these students from this left side view, which shows the similarities of students based on their temporal communication patterns. In this view, each cluster is generally arranged from left to right. However, we can see the blue cluster is separated into two clusters. We select these two as the new clusters. In the node link diagram, these clusters are clearly separated into the two strongly connected regions at the top and the bottom of the view. We also can see that the two clusters have different patterns of feature contributions across time. By looking at the histograms at each time point, we can see that they have high feature values at different time periods. Also, from the weight vector, we notice that the feature values represent the network centralities, but not gender. From these observations, the students who play a central role can be further categorized into two different groups, which have active communications at different time periods. Due to the time limitation, I presented only one example, but you can find more cases in the paper. One of which we provide an analysis of large-scale log data obtained from the supercomputer K. You can also find a qualitative comparison of the two-step dimensionality reduction to other methods. Finally, I'd like to conclude my talk. This work presents a framework called MulTiDR, which has two functionalities derived from a two-step dimensionality reduction, contrastive learning, and interactive visualization. We use MulTiDR to analyze multivariate time series data. However, MulTiDR can analyze any data that can be represented as a third-order tensor. Lastly, the source code is available on GitHub. Thank you for listening.